Good evening. A very warm welcome to you all to our second international webinar on New Horizon Chemical Challenges, Strategies, and Recent Advancements in Global Perspective, organized by Department of Chemistry in collaboration with IQAC, Government General Degree College, Shingur, Hooghly. Our college was established in the year of 2013, and now we are successfully running UGCBCS courses in 17 different disciplines of science and arts in our college under the affiliation of University of Bardhaman. Our department has started its academic journey in the year of 2013 and hope you have enjoyed a virtual visit to our department through Google slideshows as shown earlier. Now, today I am glad to inform you that today we have two distinguished speakers among us. Our first speaker is Dr. Ankunda Choudhury from Research Institute of Grain Science and Technology, Suzuka University, Japan. And his topic of illustration is on recent trends in nanotechnology-based approach for virus sensing. And we have Dr. Dhibarati Bhandabaddha from Indian Institute of Technology, Kanpur, and she will talk today on structure, function, enzymes, and proteins. The basic motto of our webinar is to enrich and enlighten us from the very basic code of some challenging chemical problems. And we have our speakers with us to share their hand-in-hand research experiences with us. Once again, I thank you, I welcome you all, our respected speakers, our honorable principal sir, our IQAC coordinator madam, our convener sir, our advisory board members, our organizing secretaries, and dear participants who have registered and joined today. Hope you will enjoy this webinar and your questions are always welcome. So please put your questions in the chat box and we will try to address all your queries before our speakers. Before proceeding to the main session, I am here to sum up the basic rules and regulations that we all have to abide by today. For smooth transition of today's webinar, participants are requested to please switch off your audio and video and not to share your screen. Please, you do not need to put any welcome message in the chat box. Just put the questions in the chat box. We will try to address your questions. And at the end of this technical session, please have a look at the chat box to have feedback form link. After filling up the feedback form link, you will have your e-certificates within next 7 days. But please note that no feedback link will be given via email. So please note the feedback form link and hope you will enjoy today's webinar. So now it is the time for official inauguration of today's webinar. So I welcome our honorable principal sir, Dr. Shantanu Chakraborty for delivery welcome address. Over to you, sir.
Thank you. Department of Chemistry, Government General Degree College organized. This is the second international webinar. Today's topic is New Horizon Chemical Challenges, Strategies, and Recent Advancements in Global Perspective. It is indeed an honor to be able to witness a webinar where emerging scientists are showing their hard work in their area of research. It is an initiative on the part of Department of Chemistry, Government General Degree College, Shingur, in collaboration with the IQAC Government General Degree College, Shingur, to identify and encourage these scientists with immense potential to contribute positively to the betterment of the society. Department of Chemistry, Government General Degree College, Shingur is committed to provide value-based science education in students coming from various socio-economic backgrounds across the state of West Bengal. The core objective of this virtual event is to provide a platform to the PhD scholars, researchers, academicians, scientists, and the future scientists for a fruitful scientific exchange with zero capital investment and also to develop their scientific aptitude. Our first speaker today is Dr. Ankunda Choudhury, who is an assistant professor, Research Institute of Green Science and Technology, Shizuoka University, Japan. Dr. Datta Choudhury was the JSPS postdoctoral fellow at Research Institute of Green Science and Technology, Shizuoka University, Shizuoka, Japan. His topic of presentation will be recent trends in nanotechnology-based approach for virus sensing. The second speaker of this evening is Dr. Dhibarati Bhandabaddha from Indian Institute of Technology, Kanpur. Dr. Bhandabaddha was the postdoctoral fellow of Institute for Cell Biology, Philips University, Marburg, Germany. She completed her PhD from Indian Institute of Science, Bangalore. Her topic of presentation will be structure, function, enzymes and proteins. There are numerous students presently participating in this webinar as audience, who I firmly believe will be enriched by listening to our honorable speakers today, and also from the input given by several eminent personalities whom we have in our midst in this evening. I extend my best wishes to all of them. Thank you.
Thank you, sir. Thank you very much. Now I welcome our IQAC coordinator, Madam Dr. Chaitali Choudhury, for welcome address. Over to you, Madam.
Good evening, everybody. On behalf of IQAC, I welcome you all in this international webinar on New Horizon Chemical Challenges, Strategies, and Recent Advancements in Global Perspective, organized by Department of Chemistry, Government General DC College, Shingur. It is worth mentioning that the Department of Chemistry is organizing international webinars on various important issues in this alien situation. The distinguished speakers today are Dr. Ankunda Choudhury, Assistant Professor, Research Institute of Green Science and Technology, Shizuoka University, Japan, and Dr. Dhibarati Bhandabaddha, Postdoctoral Researcher at IIT Kanpur. You are welcome. We are fortunate enough to hear from you. Thank you very much for facing this occasion. And thank you, Department of Chemistry, for this endeavor. Thank you all.
Thank you very much, Madam. Now it is time for actual technical session, and our head of the department, our convener, sir, Dr. Amrit Krishna Mitra, will chair this technical session. So I welcome our convener, sir, for today's webinar. Over to you, sir.
Good morning, good afternoon, and good evening to all of you wherever you are. Thank you, Professor Jayashree, for your greetings. It is a great privilege for all of us to have all of you amongst us on this particular platform. What a unique assembly today. All of us seated at various parts of the globe, but are digitally connected today. Thank you all. I take this opportunity to thank Dr. Shantanu Chakraborty, Principal, Government General Degree College, Shingur. I would also like to express my gratitude to Dr. Chaitali Choudhury, the Coordinator, IQAC, GGDC Shingur, for giving us the opportunity to conduct this webinar. I would also like to thank the organizing secretaries, Dr. Bunkim Ghosh and Professor Jayashree Sadhuka, for their contribution to this program. My sincere thanks to Dr. Shubhendu Maiti, Dr. Alokesh Hajari, Dr. Monohar Hossain Mondol for all their supports and valuable suggestions. On having a look at the list of participants of today's webinar, it gives me a great pleasure and honor to say that we have many distinguished and eminent scholars amongst us. I pay my humble regards to all of them. The speakers of today's webinar are not only eminent and successful researchers in the field of chemistry, but are also my dear friends. They have always contributed to the scientific community with their utmost sincerity, and commitment. It gives me a great pleasure to introduce them to all of you today. Their sincerity and dedication towards their work is exemplary. In order to be successful, every human being must toil and persevere. Our speakers today have known this struggle in their life and have emerged victorious against many an obstacle with courage and tenacity. The first speaker of today's webinar is Dr. Ankunda Choudhury, Assistant Professor, Research Institute of Green Science and Technology, Shizuoka University, Japan. Dr. Datta Choudhury was the JSPS postdoctoral fellow of the same university. He was the former postdoctoral fellow at Professor Dung Lab, Institute of Environmental Engineering, National Chiao Tung University, Taiwan. He completed his PhD from Shaha Institute of Nuclear Physics, Kolkata. Dr. Ankunda Choudhury has published more than 30 articles in peer-reviewed international journals with H-index of 17 and over 850 citations. He also published 2 book chapters. May I now welcome my dear friend Dr. Ankun to address the technical session 1. This web platform is eagerly waiting to listen to you. Over to you, Ankun, please.
Hello.
Yes, audible. Yes, audible.
Okay. Just hold 1 minute.
Okay.
First thing is that I want to share my slides. You know how to do this thing?
Okay. You just go to the present now. It will be on your right hand side, right hand bottom.
Okay. Now it's okay?
Yes. Just try to make it a full screen.
Okay.
Go to slideshow.
Okay.
Yes,
now it's
okay. Perfect.
Okay. But I can't see anything in Google Meet.
Yes.
Okay. It's little.
This is the problem of Google Meet.
Okay. Thank you, Amrit. And
okay.
Thank you all of the organizing committee. Actually, I couldn't see myself, so it's very difficult. And this is my first time I'm going to present something on this web platform. I mean, without any direct interaction. So I am little worried about that. Whatever. So first thing is that I definitely thanks to Amrit. He's one of my very good friend and all the organizing committee to provide me this nice opportunity and the platform to share my research and some basic concept of nanotechnologies. So my title is little general title, like recent trends in nanobiotechnology or nanotechnology based approach for the virus sensing, because now actually I am working on the different virus sensing methods. So that's why. So first thing is that this is my just a pathway. I did my BSc. I completed my BSc from Calcutta University, then MSc, PhD in nanoscience. So my basic, I'm a basic chemist, but now I'm working on a little biological field. So now, truly I am just an interdisciplinary section of biology and chemistry. So if you have any question anytime, you can stop me. So that is also okay for me, because first thing that I need to clear that Amrit told me to give a detailed slide or the presentation about my research, but intentionally make it little general, as the most of the students can relate with their studies. So that's why. So this is the outline of my presentation. So as the virus or the nanotechnologies may be little bit different or some odd from the core chemistry. So some introductory part, and then the current status of the virus sensing platform in the world now. Then my goal, our lab's goal on this point, and then our lab is developing some new materials or some different technologies for the sensing things, especially the biosensing. And we generally use some optical, light-induced methods, or some electrochemical, electrical things to detect the viruses. So, and the last, the confusion. So the first thing is virus. I mean, I think it's and the present situation, everyone is very much worried about the virus because of the corona. But still, this is just an introduction. I mean, like a virus is a particle. I think just 1 minute. Can you see my?
Yes, perfect. Perfect.
Okay.
Yes.
Okay.
Yes.
So, I mean, the virus is just a molecule, maybe it's a living or non-living, whatever. So, it contains some genetic code like RNA or DNA and covered with sometimes envelope, sometimes not, some proteins also, any membrane. So, when it it can infect some body like human body or some other things, so then it can replicate the DNA or RNA and produce some damages on the cell line. So, this is the normal things. So this is the epidemics or the pandemic situation, like different caused by different type of viruses like cholera, Zika, different type of. There is a lot of viruses. So I copied that code from that Nature Review Microbiology. That if all the virus particle, if we light just one by one, end to end like this, so it can stretch like 100 million light years. So this code is just only to imagine that how many virus particles exist in the world. It's a huge. So the thing is that it can, a loss of people and loss of money also. So just for this pandemic situation. So in that case, first, like we already facing a huge virus pandemic situation like now, that is the COVID-19. So this is the infection at January of this year, and this is March, and this is the May. So you can just imagine that how these type of viruses can spread within a few months and can damage the whole economy or the situation all of the world. So mainly we can see that this is a high mutation level of that virus. Not only COVID-19, most of the viruses have this type of system inbuilt in their body, that is high mutation level, and the extremely contagious and the speedy infection of these things, and the modal travel, that is obviously a important cause for these things. And this is one of the renowned website, that is World Meter of Viruses, the pandemic. In here we can see the India is the second place, and that is not a very good sign. So this is the scenario of the COVID-19. So just from these slides, we can imagine that the virus spreading or the virus contamination is a very, very dangerous for everyone. So the question is how to prevent this work. So in that case, yes, I can maybe use the pointer here. Yes. So in that case, the simple thing is that we can stop the transmission. This is the simple way. Like lockdown or something, that is not an easy job. And treatment, there is actually main treatment is vaccination, and that is not very easy or very rapid process. Like COVID-19, we're still struggling to develop the vaccination. So in that case, the treatment is the only thing, and the symptomatic treatment. If you have fever, you can take the fever's medicine like this. So for that, the diagnosis thing is very important. So in that case, the problem is the diagnostic. All the viruses, different viruses has generally the common symptoms, like diarrhea, some fever, headache, all these things, almost common. So it is very difficult to identify the viral infection in a proper time. So we can initiate the treatment process. So there is a crucial parameter, the crucial thing to prevent the virus outbreak. But the problem is the identification is not an easy job, and that is our goal. So in that case, we generally use the whole virus detection method in two parts. One is the direct method, and another is the indirect method. So in direct method, we can directly detect the virus or the inside RNA or DNA, or the protein, the capture protein or the capsid protein of the virus. So this is the we are trying to detect the virus itself. And the another thing is that the indirect method, I mean, when the virus is already infected some body, and then the body can already produce some antibody, then we can track the antibody. So, I mean, this much of antibody means the virus is infected like that. So the thing is that reliability of these methods, like indirect methods, are relatively low, but difficult. I mean, this method is not maybe so difficult. The difficult method is direct sensing. I mean, the virus isolation or virus detection. But this is also very difficult, but it's a reliable method. So the issues is, I mean, definitely we can. Our lab, I'm really trying to develop something on the direct methods like virus or the genome or something. With, I mean, not any expensive. No, I mean, it should be very, rapid, but very inexpensive, and the data should be the highly reliable with a high sensitivity. So in that case, I'm just giving some example of the dengue. This is just a dengue figure. Like initial day of the infection, generally the protein that is here for dengue, it is NS1, or the viral particle is very high, the initial stage. So after that, this antibody generation is started. So if we focus on the antibody generation, generally after 5, 4, 6, or 7 days of infection is fine. But the case is like after 5 or 7 days, already the body already damaged, severely. So if we can detect very initially 1 or 2 or 3 or 4 days, that will be really better. So in that case, generally we try to make some detection kit or something which can detect the virus within the infection of, within the infection of 3 or 4 days. So that will be the very nice time frame. So if we can really detect in that time frame, so we can initiate the treatment very early, and definitely the fatality rate should be very low. So this is our aim. So in that case, now our existing methods which are really available, or we can really rely on that thing, is mainly this type like virus culture, Western blots or something. And in this case, mostly 2 methods are very much famous. One is ELISA and one is PCR or maybe RT-PCR or something. So in that case, we generally, in ELISA, we use the antibody screening, the detection of the antibody. And the PCR is the directly genome, the DNA or RNA reading. So like that. So in that case, if we develop some detection kits, we can rapidly measure from any, the background maybe any of like PCR or ELISA or some new method or new technologies. That will be really a good option. So already we have some this type of things like, all these are actually the presentation of biosensor. Like this is a glucose sensor. We all know these things. Pregnancy case, lactose meter to detect the lactose in milk. Or always, also we have that already some viral detection kit also, like dengue virus kit is there. So COVID also is there. But the thing is that everyone knows that the reliability or the authenticity of these methods is not so good. It's still poor. So in that case, still we use the glucose meter, but if we really want to know the exact sugar level in our blood, we generally go for the diagnostic center, not rely on the glucose meter because of the poor reliability, the fluctuation. So in that case, our challenge is try to improve some methods, some new technology or materials which can show a very stable signals for that thing. So in that case, the nanotechnology comes. So we use some different nanomaterials to make some reliable techniques or reliable things, or some technology or some materials which can generate some steady signals. So nanomaterials is very common. I should not maybe go for a detailed things about what is the nanostructures, but in common thing, it should be less, between 1 to 100 nanometer in dimension. So when any bulk material can go below the 100 nanometer, it can change its property or it can enhance its every properties. So we can use that property for the applications purpose. So this is few examples from our lab, like some iron oxide nanoparticles, which have the magnetic properties, gold nanoparticles, carbon nanotubes. We also use some graphene. This is just a carbon matrix. and some quantum dots, inorganic or graphene quantum dots like this. It has some good optical and electrical properties also. So we can use that properties for the sensing purpose. So in that case, generally for basic things, we can use the gold nanoparticle, because depending on the size, it can change their color. That is a very nice phenomena. And another thing is that different inorganic quantum particles we can also use, because this particle has a strong fluorescence with different range, and we can also control them depending on our demand or requirement. And another thing is that this is some liposomal matrix or polymer cage matrix, so which can accumulate different type of probe, like fluorescence probe or electrochemical probe, anything inside it. So this is some type of cage structure. So we can use this type of system also, and definitely there are a lot of things. But this is the basic things which we can use for the biosensor things. And sometimes for the higher level of detection or the sensitivity, we can use some advanced nanomaterial also. So in this section, we use some metal organic framework type of things, which is coated with some carbon things, and the matrix is carbon. So and then we add some platinum nanoparticles on that. So when we decompose this whole system in some heat, in presence of a high heat or something, then carbon matrix is slowly vanished. So we can get some mixture or some nanocomposite of platinum and the Z for cobalt, some oxides, with a halo space. So this halo space can give some more interaction between the analyte molecules or the virus or some other things. So it can enhance the properties. It can enhance the sensitivity also, the interaction. So this is the simple some techniques that how we, after generally, if we are going to do something on very basic nanomaterials, then the characterization is not maybe very important. But if this type of advanced nanomaterial, first we need to confirm the structures. So for these things, we use this type of transmit an electron microscopy image or the STM image, just to show that this structure is well synthesized like that. So this is the nanomaterial. So we can use this nanomaterials for different application, like the biochip, drug delivery, imaging, even cancer treatment. But we generally use these things for the sensor or the biosensor. The simple concept is that it should be like without any signal. When it has some analyte, it can produce some signal. It may be light, it may be color, it may be some electrical response, whatever. So this is the concept. We generally use some basic methodologies, because our job to make some new technologies or make some new materials which can be used for the application. So this is the biosensor. The concept is like that. Here some analyte we can just insert in our system. It can recognize, and then some transfer of this system to a detectable one. So this transfer is called the transducer. Actually, we are working on this portion. Some materials which can transduce the signal of the analyte. If the analyte is present, it can transduce the signal to an optical or electrochemical things. So that's our work. But the work is not so simple as I said just right now. So this is a scheme. This is our pathway, how to really go for a application. Like the red one, the middle one is our lab. Actually, the lab is the main head of the lab is Inoch Park, my senior professor. And we have a separate team for the nanotechnology also. So we generally have some collaboration, mainly in Japan and sometimes in outside of Japan also. So here we can get some viruses, some antibodies, some clinical trials also. Like one, Dr. Prabhash Kumar Shaduka from ICMR NICED also, they also have a good collaboration with us, that we can get some mosquito-borne viruses from them, because the dengue, chikungunya, or not malaria, like Zika, these diseases are not common in Japan, so we can get the samples from this one. So, a lot of process is there to make a real biosensor, to establish a real biosensor. So, now I am going for the main things that what we really work from that. So this is a simple technique, the optical sensor, that is a colorimetric. So if there is a virus, we can get some color. If there is no virus, no color. If the high concentration of virus means a high intense color, like that. The concept is, it's is like a very small well, like a micro pellets or like this. So we first entrap the antibody, the specific antibody for some specific virus here. Then we block with some BSA. Just, now this platform is only can conjugate the virus, the opposite of this antibody, like this virus, on the antibody surface, not in the surface or the any other part of the biosensor. So then the virus is captured here. After that, we can add some gold nanoparticle, the simple one, and then we can generate some in situ silver coating on the gold nanoparticle, so that this system can change the TMB reaction. TMB is a good optical sensor. In presence of peroxides, it can change to its formation to an oxidized form and make some yellow color. So already this is established that in presence of gold or silver type of nanomaterials, this process is very rapid. So we are using that thing. So this is the basic concept of the ELISA. So we are just trying to update or upgrade the ELISA process. If the virus is there, then a small number of virus also can maybe give some good color change. So this is the concept of this, and for this initial characterization we can get the gold image, and after the coating of the silver we can get the very good core shell structure. So this can be core silver, and this maybe the inner, should be the gold one. So this is the result where we can get that the HEV, this is the hepatitis E virus. This virus, this is not exactly virus, this is a virus-like particles. Not is the infected one. So we can handle it in our normal lab also. So this virus can have a very strong signal and a very yellow color, where the other viruses or the blank, there is no color. So that's the main concept. And we compare with the normal ELISA also. So this is the normal ELISA, and this is our method. And this method is really very, very good, compared to normal ELISA. So one of our PhD student, Indra, he actually did this work. So in that case, after that, we just try for the real sample analysis. So this is first we just took a healthy monkey and infect the HB virus to that. So after some days, we just collect the samples, the virus samples from that, and then two portions. One portion is going for the RT-PCR analysis, which is the gold standard for any virus sample analysis, and another is our method, and we compare that thing. Because most of cases the virus detection things are okay for the normal process, but not in the real samples case. So in that case, we generally use these things. So we just compare our data with the RT-PCR and check the trend. I can't say that the trend is very much okay, but it's okay. It can acceptable. Definitely, we need to develop more and more and to accurate this method. So this is the thing of the calorimetric sensing. Obviously, the sensitivity is not too good, but it's a very easy job just to recognize the virus in naked eye, just a color change. So in that case, for the better sensitivity, we shift to the fluorescence imaging, fluorescence sensing also. So in that case, normal fluorescence molecule can be used, but we used here some developed mechanism that is called the localized surface plasmon resonance. So in that case, we need some fluorescence molecule here, like the quantum dot. This is the inorganic quantum dot, which has a very good fluorescence. But in presence of some surface plasmon molecule like gold nanoparticle, silver nanoparticle like this, if it is very close, closely situated, then it can show some quenching, reduce of the fluorescence. If it is situated in a certain distance, it has some good enhancement. So that is we call an LSPS system. If it is too far, then there is no effect. So using these two things, like very close or little measured distance between these two molecules, we can optimize the system. Sometimes it's enhancement, sometimes it's the quenching. So in that case, we develop some LSPS system between the gold and the quantum dot, And here the cross-linker, I mean the distance between these two molecules is controlled by different size of the peptides. So peptides, we imagine that peptide can also be, I mean, make some sizes. So in that case, I just make the structural things of one peptide, like this one is the terminal is 1 cysteine, and another like for this SH bond, and the another term it contains some K, I mean, and the middle portion has some lysine molecule also, I mean amino acid also. This is for the antibody conjugation, this extra carboxylic group. So this every, I mean, this is a different length only. We use the glycine for the chain length, and this every peptide contains two extra amino acid. This is for the antibody conjugation, and one ended for SH, which is the gold nanoparticle, and another is NH3 for the quantum dot conjugation. So in that case, this portion, this is, I mean, covalently bonded with the quantum dot, and this portion is just gold and SH bond with the gold nanoparticle. So in that thing, we just change different variation, like different peptide length. It can, this is the different peptide length. So small length to high, I mean the bigger length or the longer length, and different size of gold nanoparticle also. There is a small gold nanoparticle to very big gold nanoparticle. So in that case, we generally conclude some trend that if the big gold nanoparticle is there, so generally quenching is, I mean, mostly happened. But in case of small one, the gold nanoparticle, where the quantum dot side is always fixed, generally the enhancement is occurs. And the same thing, if the particles are very close, the quenching is there mainly. And if the particle is very well distant, then the enhancement we can notice. So this is the optimization process. There is 36 combination of the gold nanoparticle CDSE system with different gold nanoparticle size and different chain linker. So after that, we simulate the whole structure, that we assume that these particles are, this particle has some, like, we assume that this particle has some 7.5 nanometer of distance peptide, but maybe it's actually not. So that's why we generate some simulation software and try to estimate the actual length, and which is almost close enough with our cumulative distance of this peptide. This is the tame image of this quantum dot and the gold nanoparticle. We can see the gold nanoparticle and quantum dot situated very closely, and we also check their fringes to confirm the exact structure. So after that, we use this sensing, and use this nanomaterial or the nano conjugate for the sensing application also. Like this is the gold nanoparticle and quantum dot and the peptide. So we use this 2 carboxylic portion for the antibody conjugation. So after that, we can use the specific virus for that one. Here, another system, we can use very small length of peptide. So here, this is very closely situated, and again add some antibody there, and then again for the virus detection. So in that case, where this system is this length is almost 7.5 or 8 nanometer, which is a very good for the LSPR fluorescence enhancement. We can have some good enhancement in that case. But after that virus attachment, this LSPR system is blocked. So after that virus attachment, we can have some gradual signal decrease. And in that case, here the 2 molecules are very close, so there is a strong quenching effect on that. But when we add the virus, it can also interrupt the quenching effect, and then we can recover the fluorescence signal. So this is the some results of that. Right here, the long system, which is good for enhancement, which have some initial good fluorescence property. So after adding different concentration of virus, it can slowly, making some quenching effect. Similarly, this is the opposite one, which is a very close situated one, which have some quenching. So after adding the virus, it can have some gradual increment, and it also maintains some calibration, the straight line. So from this straight line equation, we can also predict, or we also calculate the unknown concentration of optimize different different loading of the antibody also. We just change the peptide structure with single antibody or double antibody or triple antibody. And after the optimization, we get the best result in the double antibody. And the last one is the very important thing for this is the selectivity. I mean, this system also applied from different other viruses like Zika. This system is for influenza, and we can use this system for other viruses and other metal ions, amino acid, and all those things. But definitely, this green one is the main target, and the sensitivity or the selectivity of the sensor is very good compared to the other things. So in that case, we just use the same principle for another thing. I mean, the previous one is for direct virus sensing, and the next one is the DNA sensing. So I mean, in that case, we just use the extracted RNA from the dengue virus and use for the serotype detection. I mean, what is the serotype? I mean, this is just a different kind of the same dengue virus. I mean, we have now and presently we have maybe 5, but the 5th serotype is not well established. The 4th serotype is very available, or dengue 1, dengue 2, dengue 3, dengue 4. So in that case, this is this is newspaper cutting from a Calcutta Times of India. We have some serotype problem also. Like one person is already affected by dengue 1. Again, he can affected by the dengue 2 also. So this is a secondary infection, and this is more fatal. So in that case, it is also important to recognize which type of virus is there. Like dengue is okay, but which type of dengue? So this is called the serotype detection. So in that case, we also try to establish some mechanism. Here we use some molecular beacon. So in the actual concept is the same, like the LSPR. So in this molecule, this is the probe DNA, which is this red part or the blue part is the exactly opposite to some dengue 1 or dengue 2 DNA. And now this is a molecular beacon formation. I mean, the end is already conjugated, and the fluorescent molecule is tagged with there. So after addition of some analyte like dengue RNA or something, this dengue RNA, when it's completely complementary with this loop formation, it can open up the loop and make this linear structure. I mean, not exactly linear, but it's more or less linear structure. So there is 2 conditions. One condition is for dengue 1 or dengue 3 like that, and another is the dengue 4 or dengue 2. In that case, in one scenario, the quantum dot and gold is far, like 14 nanometer like this. And in second scenario, it is very close, like 3 nanometer when it's open. So it is expected that it is when it is a very far, it can get some good fluorescence. When it is very close, it can have some quenching effect. So from this different type of effect, we can recognize that which type of serotype is there. So before proceeding to that, I mean, when we are synthesizing this probe DNA, we also we have some simulation to confirm the probe structure. So this is the result. But this is the dengue 1. We just add the synthetic RNA also, to the sensor probe and check the enhancement is periodic or not. We can maintain the calibration line or not. So dengue 1, dengue 2, dengue 3, different 4 type of. We can see that dengue 3 and dengue 4 have periodic, some quenching effect, where the other 2 have a very good increasing order, the fluorescence LSPR. So after that, we can make some system where we already develop 4 type of probe DNA and the 4 type of analyte also, and make some calibration that when the dengue probe is there, it can particularly recognize the dengue 1, not the other 3 one. When the dengue 2, it can also detect the quench, the dengue 2 only, not the others. So this is the selectivity. That probe is only very much specific for that type of RNA for the samples. Then we switch to the next one with the real sample, the dengue RNA. This is also, this is almost the same trend, but not as good as the synthetic RNAs, because this is a real samples. So real dengue contains a lot of other interference also, which can maybe decrease the sensitivity or the signal amplification. So, and this is the analytical terminology of the LOT. That the system, the sensitivity in terms of LOT, the limit of detection, that is quite high and quite good also. So in that case, if we from this optical measurement only, we can say that the optical measurement is very nice. It's a very easy to handle. It has some good sensitivity also, and Sometimes we can reach the PCL level also. And PCL level means the best one, the gold standard level. But the thing is that, I mean, this is also sensing is rapid, but the problem is the optimization is not an easy one. This is a very crucial step, and definitely sometimes we can reach the PCL level, not the every time. I mean, most of the time it's not. So in that case, I mean, another important thing is that the reliability. What I already told the initial slides, that still the reliability is not a, I mean, very considerable. Like we can blindly rely on this data. It is not maybe possible on the fluorescence or the colorimetric system. So in that case, we try to develop some other method where we can use the electrochemical sensing method. So here, I mean, like in that case, like colorimetric, the transducer can generate the signal in terms of color. In fluorescence, in terms of fluorescence. But in electrochemical sensing, the ultimate signal is some electrochemical response, like or electrical response, like current or resistance or something. And before wire addition, it has some maybe low resistance or maybe low current. After the wire addition, it should have the good current or good resistance or impedance, like these things. So in that case, actually electrochemical sensing is a more sensitive. That is a good advantage. Another thing is that if we can use the both system, like the dual sensing on the same platform, and the analyte is also same, but we can have the two signals. So this is called the dual sensing. So we can double check our results, and it can make the more reliable data. So that's the main thing. So in that case, this is a simple thing of a dual mode of sensing. Like this is a virus. We can attach some magnetic nanoparticle just to extract or isolate the virus with another antibody conjugated system, which contains the probes. Like this probe can be used for the optical and the electrochemical both ways. So in that case, first we magnetically separate the virus, and then we can bust the cage structure or this. I mean, maybe if, it can be a liposomal or some other cage structure, and we can bust out the inner things, which is the signal, like optical or something, and then we can calculate the approximatory virus from the pack calculation. So in that thing, this is one method that is with the liposomal matrix. Like we just synthesize a liposome with two type of probe. One is the hydrophobic things, which as a liposome is some molecule which have a hydrophobic layer, and inside is a hydrophilic. So we use some two things, that hydrophilic probe that is called the methylene blue inside this, and some hydrophobic quantum dots which has a fluorescence in the layer. So this type of system, it has two sensing parameters. One is hydrophilic methylene blue for electrochemical sensing, and the another thing is the hydrophobic quantum dots for the fluorometric sensing. So the same thing can attach with some virus. Here actually we represent some chikungunya proteins in that work, and some magnetic nanoparticle for the sandwich acid, like magnetic nanoparticle, then the virus, and then the liposomal structure with these two probes. And then after isolation of the whole system, we can bust out the system, and that encapsulated methylene blue and the quantum dot, they can give the signal in the fluorometric and electrochemical. So this is some basic characterizations on that, and this is the sensing results. Like the sensor in the fluorescence, initially there is no response, no fluorescence. After adding the different virus and then bust out the liposome, the hydrophobic quantum dot is released and makes some fluorescence signals, and it also maintains some linearity. Same thing, when after bust out, we can check the DPV signal. DPV is a parameter for differential pulse voltammetric. This is a parameter for current and current response, and we can see that when the virus concentration is low, we have some small signal. When the concentration is increasing, the signal is also increasing and trending with a smooth calibration line. So it means the system is working in the both system. So another thing is that the similar thing is little more complex from the previous one. Here we also use the quantum dot, and after that we use some magnetic layer, the iron layer. Then we heat the magnetic layer, and this magnetic iron just formed to the oxide, that is the ferric oxide, which has some magnetic properties, and it makes some exactly not hollow but hollow kind of structure. So there is some structure which inside there is some fluorescence property. So overall the molecule has a magnetic property also, and inside there is a quantum dot contains the fluorescence property. Then we use the antibody coating on the surface and used this whole system, this nano conjugate for the virus sensing. So imagine there is a container which has a lot of interference and the virus. Then we add this system as the antibody can capture the virus. Then we magnetically separate the whole systems. So in that case, the magnet can separate the nano conjugates and the virus. Some nano conjugates is also there, which is not maybe attached with the virus. They can also attach to the surface of this magnet. So then we can use another electrode, which is also the antibody conjugated, and dip on the solution. So in that case, only the virus attached my molecule, the nanocomposite, can attach on the electrode. And the rest, others which are not attached with the virus, they remain in the solution. So from this solution, we can get the fluorescence and get the back calculation. If the virus is high, then the free molecule is low. If the virus is very low, then the free molecule should be high. So from this back calculation, we can calculate the fluorescence detection, the concentration of the virus. And from this electrode, we can have some impedance spectra. So impedance spectra is like a resistance spectrum. So if the electrode has nothing, like only the conducting layer of something and antibody like that, then we can have some good response, small resistance value. If the virus is there, as the virus is a big molecule without any conductivity, so it can increase the resistance. So it can increase like that. If the small virus has small impedance, if the big amount of virus is there, it has a higher resistance. So in the same system, the same molecule actually using for the two systems. One is the electrochemical and one is the optical. So one of our lab mate, Akhilesh Gangan Moina, he did this work mainly. It's also a very nice work. So this is a simple characterization where this is the quantum dots. After coating with iron, you can see the dark color and a bigger size also. So when we oxidized and it formed the iron to the iron oxides, there may be created some hollow space inside that quantum dots. The iron oxide nanoparticle. So this is the high resolution image just to check the fringes of that structure. So this is the results. The same trend is like that. If the virus concentration is very, this is the impedance sensing where the virus, this is a normal sensor. After the addition of the virus, the impedance is just increasing, and that. And we have the calibration also. And another thing is that this is a back calculation method where the virus is very small amount, then the fluorescence is very high. When the virus is increasing the concentration, and this is a back calculating method, so the signal in the fluorescence is going down. So this also has some good linear trend. So up to now, this is all about the electrochemical and the optical, fused method. But still, we are not satisfied, definitely, because the sensitivity. In that case, as the method is a dual method, so we have that, we can reach that reliability, definitely. But still, we are struggling on the sensitivity because some virus molecule is like that, which can fatal for only 2 or 3 or few number of virus particles. So in that case, the system is not maybe good enough. So in that case, we develop this type of method, which is little advanced from the normal electrochemical methods. So here, initially, we just use some electrode and coat with some conducting layer. Here is the polyaniline and gold polyaniline matrix. This is a very good conducting matrix, and it can also attach with some graphene quantum dots, which is attached with the antibodies. So it's look like this one, the electrode and some conducting polymer matrix with gold and the GQDs. This GQDs contains the antibody. So it's a very nice, it can also attach the virus. That is fine. This is the conventional one. But after that, we use here the pulse, the electric when we incubate this electrode in a viral solution, we use some external pulse on the electrode. So on that thing, we observe that the virus accumulation and the sensing and the signal is very much higher than the normal one, the normal imperimetric methods. So this is the, advancement of this technique. After using that pulse, we have the better sensitivity. So this is the gold polyaniline. When we use the gold polyaniline, the gold is separated on the surface, and therefore the antibody also entrapped on different portion of the electrode surface with a homogeneous manner. That is a good important thing for the sensing application. And this is the graphene quantum dot stain image. So in that case, we compare with 0 volt. If there is no pulse, we also still have some results. If there is a pulse of 0.8, something which this is the optimized condition, and this is a high amount of pulse also. So when there is no pulse, we also have something, but in very low amount of virus, like 1 femtomolar or 10 femtomolar, this type of things, femtogram per ml. So the difference of the impedance is very small. But in case of some pulse, then the difference is very higher. So with the help of this pulse, we can reach very low amount of sensing also. But in case of extremely high pulse, definitely we have something, but the higher concentration of the virus has some problem, and the electrode is also destroyed in presence of high amount of the voltage. So that's why we also check the different voltage for the pulse, and we optimize that the 0.8 is the best one for our sensing things. So the same method, because this is the ultimate goal, just compare with the RT-PCR, the same monkeys, same type of methods, and we collect the samples for these two methods and check the trend. And definitely in this case, we get the better results. And this is our method, the red one, and this is the black one is the RT-PCR, and it is almost comparable. So from these things, we can say that yes, our method is okay for to replace the RT-PCR, but it is not like that. It's too early to say like that. We have some other things also, some interference and all those things for the real sample analysis also. After that, maybe we can challenge. So this is the conclusion. Ultimate goal is the device manufacturing, but this is not our duty. Our job. We have some collaboration with some company. We can make the device, but the protocols or the materials, this is our job. So we are preparing that things and transfer to that technology or the materials to that company for the ultimate device fabrication. So we are still ongoing on that thing. So still the question is the reliability and the high sensitivity. RT-PCR, to replace the RT-PCR, maybe we can sometimes rely on the LSPR based fluorescence system, but not all time. So sometimes we need to use the both sensing method for the more reliability or the authenticity. So that's the all things, and thank you for all. For your patience, and this is my acknowledgement signs. The first layer is my CST in the Chemical Sciences Division, SINP, where actually I started. I really become a researcher in that level. These people really helped me a lot. After that, I moved to Taiwan. This is my Taiwan supervisor, and here is Akhilesh Gangan Boyna. He actually still working on with me in our current lab. He also switched to Taiwan to Japan now. He is my recent supervisor, and this is our colleague. Actually, these people, we all are working on the nano bio lab for the developing on different type of sensors. So thank you all.
Yes, thank you, Ankun, for delivering such a wonderful lecture. Thank you very much. You have enriched all of us through your enthralling presentation. Thank you, Ankun. Thank you very much. Actually, we are having some questions for you. Should I proceed?
Mm-hmm.
Okay. There is a question, I think, from a student that what is quantum dot?
What is quantum? Okay, that's nice. Actually, when there is different type of nanomaterials, like I already told that nanomaterial should be less than 100 nanometer in size. Any of one direction. Every particle has 3 dimensions, like X, Y, Z. So if there is one dimension is less than 100, so it can be like a sheet, like a plane structure. If the two dimension is below 100 nanometer, so it can make like a rod. So nano rod, nano wire, like this. If the three dimension is in a nano dimension, like less than 100, then it can be like a dot. So in that case, we can say that if there is a zero dimension thing, I mean all dimension in a nano, then we can say like a dot. So if you are saying about the quantum dots, so something which has some properties, generally in fluorescence, all the dimensions should be less than 100 nanometers. Then we can call it like dot.
Okay. Thank you, Ankun. And the next question is, in electrochemical impedimetric sensing method, what is the concentration of AUNP?
Okay, very nice. Actually, this is a little detailed question. This is initially we optimize the gold nanoparticle concentration also. Amrit, can you see my presentation also? No.
Yes, it is visible.
In that case, like this portion, actually we add the gold nanoparticle.
Yes.
Gold precursor is there, the gold chloride, and we use the aniline to oxidize to reduce the gold chloride to gold nanoparticle. So initially we use some less amount of gold nanoparticle and try to make the polyaniline, gold polyaniline nanomatrix. So initially, and then we try to enhance the concentration also and check the surface of the gold nanoparticle. So after that, we generally optimize that if the concentration of the gold nanoparticle is near about 1 millimolar, that is the fine and the best one, to make some gold nanoparticle based polyaniline system where the gold is not too dense but is well distributed on the everywhere, every surface of the polyaniline. So this is the optimized condition.
Okay.
Is it okay?
Yes. And Ankun, I have two questions for you.
Yes.
Actually, my first question is how the pulse can generate better sensitivity in electrochemical detection.
Actually, when we are incubating the sensor electrode in the virus solution, then we generate the pulse on the electrode surface. So in that case, as the virus, first thing is that the virus already have some negatively charged surface. This is the normal phenomenon of viral. So if we can use some positive charge of the electrode, there is some electrostatic interaction. This is the first thing. And the another thing is that as we are using the polyaniline chains, so polyaniline is also a very good redox, has a very good nice redox property. So when we use some pulse, it can also expand the chain of the polyaniline. So there is on that situation, it can enhance the option to to induce or to accumulate more virus particle on the surface. So in that case, there is a multiple reason, but definitely these two reason is the predominant to make more accumulation or the attachment of the virus particle on the surface of the electrode. So that is the main reason when using that pulse, we can get the better sensitivity.
Okay. Thank you, Ankun. And the next question is from Dr. Subhash Chandra Bera, and he is asking that what should be the minimum virus load or concentration of virus particle per microliter in the sample to get a reasonable result from the current sensitivity?
First thing is this question is depend on every methods. This is varied from method to method. Like in LSPR, generally we reached for the VLPs or the normal non-infected virus, it's 100 femtomolar to maximum one, and like minimum 1 picomolar like this. But in case of electrochemical, 1 femtomolar, 10 femtomolar is very nice. Sometimes 1 femtomolar also we can reach. So it depends on the on the method also.
Okay. And the next question is from Dr. Manoj Kumar Sarangi. Can you differentiate between an active and inactive virus?
No.
What is the main con of virus you need for proper detection?
So I already asked these things. I already answered this question that minimum concentration is depends on the method to method. But if you are asking that it's inactive or active or we can't say like that, because this all things are depend on mainly either the antibody antigen conjugation or the DNA or DNA RNA the conjugation. So in these things is all related to the chemistry. So generally we use the inactivated virus form, and sometimes we send our samples to some BS3 lab also for the real samples detection also. There is no significant change on the virus activity. And if the virus is inactive or active, most of cases we get the same type of results.
Okay, thank you. And next question is from Dr. Kollol Beda. How do you calculate the concentration of different complex nanocomposite, and what is the unit?
How do I calculate the concentration of different complex
nanocomposite?
Okay. I mean, this is also very general question. Like if there is a nanocomposite, truly speaking, maybe we don't calculate the exact concentration. We generally use before the nanoconjugate formation. Generally, we used to calculate the exact concentration. Like we just, for example, gold nanoparticle and quantum dots. So in precursor state, we already calculate the concentration of quantum dots or gold. Then we assume that most of every particle already make the complex. So maybe after complex formation, we never try to calculate the concentration. And unit definitely is like that. Generally, we use for the precursors molarity, but after the nanoparticle formation, we generally check in a nanogram per liter or something like that. I mean, gram per liter or some particles per ml, like this.
Okay. And the next question is, Ankun, are there any specific health or other risks from nano products?
Nano means is a lot of things. So everything can be nano, right? The gold nanoparticle can be also formed like a nanoparticle. So the gold nanoparticle is very nice. So it don't have any hazardous things in our health. If you are taking a lot of things, so it's fine. But if you are making some nano products or nanoparticles, which is not a very good for our health, so that can be hazardous or dangerous for you. So
yes.
The nano product is fine, then I mean, if the bulk product is fine, then the nano product should be also fine.
Okay, thank you. And the last question for you is from my end. In case of real virus sample detection, what is your achievement?
0. We tried something like first thing is that real virus sample handling. I can't handle the real virus sample because I don't have that training to operate in BS3 or BS4 labs. So we generally send the samples to some other laboratories. Here, one famous laboratory is like the National Institute of Infectious Disease, NIIT. Is a very famous. They can handle all over the infectious disease. So they sometimes use, but we are slow. So when we really try to make something on some virus or something, already that topic is very much common in everywhere. So, but we are establishing that coordination with different type of organization of collaborators. So maybe in future we can get something.
Okay. Thank you, Ankun, for your time. Actually, our speakers are so eloquent and mesmerizing that we don't want to let them go. We want to continue listen to them and learn more and more things from them. However, unfortunately, since we have a limited time period, we may not be able to accommodate questions from too many participants. Thank you, Ankun. Thank you for your precious time. Thank you very much from the Department of Chemistry, Government General Degree College, Shingur. Thank you. The second speaker of today's webinar is Dr. Dhibarati Bhandabaddha from Indian Institute of Technology, Kanpur, India. Dr. Dhibarati was a postdoctoral fellow at the Institute of Cell Biology, Philipps University, Marburg, Germany. She completed her PhD from Indian Institute of Science, Bangalore, under the supervision of legendary Professor P. Balaram sir. Dr. Dhibarati has published several research articles in extremely high-impact journals. The research of Dr. Dhibarati has made a huge impact in the chemistry fraternity. Her present research is focusing on structure function characterizations of bacterial proteins. She has done a substantial research on mechanism of FES cluster biogenesis in eukaryotic cytosol and analysis of early diabetic biomarkers, albumin modification. We are very much eager to you, Dr. Dhibarati. I am sure that all the participants will be extremely enriched listening to you. Over to you, Dhibarati. This web platform is waiting for you. Over to you.
Thank you so much, Amrit. Am I audible?
Yes, perfectly.
Okay, and I think Ankan has to stop sharing so that I can start sharing my slides, I guess.
Okay.
Thank you, Ankan. Okay, are my slides visible?
Yes, Dhibarati.
Okay, then I will start. So once again, thank you, Dr. Mitra, for your kind introduction. And good evening, everyone, for waiting so patiently. And already you have heard a lot about biosensors and virus biosensors from Ankan. So from there, I take and go on with my topic, where you can see the title of my talk today has been changed a little bit. So in the flyer, if you remember, the title was the structure function of enzymes and proteins. And here I have also added one more word in the first. I'll change the pointer. Yeah. So the sequence I have included now. So this was a deliberate attempt not to put the sequence before and put the sequence now, because this part of the paradigm, so this is known as sequence structure function paradigm, which is a very well-known paradigm in the biochemical world. And I would like to show you how the sequence is one of the most important part of this whole paradigm. So first of all, to start with, since I will think that most of you are from chemistry background, and so as I till my postgraduate studies, so I will start with very basics of biochemistry. So first of all, what is the difference between enzymes and proteins? To start with, proteins are a long chain of amino acids, more than 20 amino acids together and joined by peptide bonds. And if they form some kind of three-dimensional structure, they are known as proteins. Whereas enzymes, they are also proteins, but they have an additional criteria. So enzyme can catalyze chemical reactions by lowering the activation energy barrier if you go to a reaction profile from a substrate to a product site. So that's the basic difference between enzymes and proteins. Now to start with, let's first discuss the paradigm from my title, that's the sequence structure function paradigm. So the most well-established phenomena is that which comes in 1960 from Professor Anfinsen, a famous biochemist, that all proteins will be having a sequence, as I described, a series of amino acids. For example, my name, Dhibarati, so it goes like D-E-B-A. And instead of B, if I put a V, then it becomes like an aspartate, then a glutamate, then a valide, and alanine, and so on. So this is the primary sequence of any polypeptide or protein or enzyme to start with. So once you have a sequence, that's the primary sequence, then Anfinsen suggested that the protein will take a particular structure. For example, here I showed a particular structure known as Tim barrel fold. And once the protein or the enzyme is folded to a particular structure, it shows its function. For example, enzyme catalysis. If it is not an enzyme and if it is a protein, then probably it will do like it can still bind to a substrate and gives it to another protein, but it cannot do the reaction mechanism by lowering the energy of activation. So this is a well-established paradigm known in the biochemical field. Whereas in today's world, the emerging sequence is a bit different. So once you have a sequence, now it has been already proved that it doesn't matter if you have a sequence of a protein, it has to have a structure. So it can also have disordered region, or the whole protein can also be disordered. But this disorderliness has nothing to do with the function of this particular proteins. For example, still they can do some functions, for example, binding, etc. Here I have also shown an exemplary, as shown here as P27 protein, which is a kind of kinase inhibitor, and it involves in the cell division state. For today's talk, I will focus on the more established part. And here I have shown you an example of the structural folds. One of such structural fold is Tim barrel fold. Now I chose Tim barrel fold because of the main reason that I happened to work with two Tim barrel fold proteins during my past 10 years of research career. And it was not a deliberate attempt. So it was kind of like a serendipity that I happened to work with two proteins which had this Tim barrel fold. So I would focus first on what is this Tim barrel fold and why it is so important. So here I show you various proteins from various organisms. For example, here are 6 Tim barrel fold proteins or enzymes. So what is Tim barrel fold? So Tim barrel fold is a structure which is kind of like a beta alpha folate structure. So there are beta sheets inside the protein which forms a barrel, and there are alpha helices towards the periphery of the protein which is kind of like protecting this barrel. This is known as Tim barrel fold. And the fascinating fact about Tim barrel fold structures are that if you take one organism and if you try to see what are the proteins are there inside, that's known as the proteome of that organism, surprisingly, we'll find out that most abundant fold is the Tim barrel fold. So it's a very well-known barrel fold protein. Now, if I show you only the structure, they all look similar. So we might think that, okay, then maybe their sequence and structures are same. But that is not the scenario. So if I click my mouse now, here you can see that all these proteins or enzymes I have picked up randomly from protein data bank, they are all from different pathways. Suppose, for example, this particular protein is known as triphosphate isomerase. This is a glycolytic enzyme. The second one is known as Viperine, which is an iron sulfur cluster protein. Then the next one is a metalloprotein, and so on. For example, the down one, this is also involved in amino acid biosynthesis or some nucleotide biosynthesis, etc. So for today's talk, I would try to focus on two such proteins with which I have worked on. And the first two are these two proteins. So as I mentioned already, the second one is known as Viperine protein. This is an iron sulfur cluster protein. So what does this protein do, first of all? So to remember, Viperine is not an enzyme, it's a protein. It has a 4-iron 4-sulfur cluster inside it. Viperine is a protein which expresses inside our body when there are viral infections from outside. Not coronavirus, because it's not yet proved, but other viruses such as Zika virus and so on. When they infect our cells inside our body, Viperine expresses more and it blocks the DNA replication of such virus. So this protein is very important. Now, what is interesting about this particular protein from a biochemist point of view is that this protein requires this iron sulfur cluster very much, except for the fact that this is a Tim barrel fold protein, for its activity. So today I will tell you two different proteins. One is this Viperine and the other one is the first protein, which is triphosphate isomerase. So first I go with the second one because this is I worked recently in my last postdoctoral research in Germany. So first I want to show you that since I told this iron sulfur cluster is very important for the Viperine for its activity, the fascinating fact about any iron sulfur cluster protein is that they cannot synthesize the iron sulfur cluster by their own. Now, from chemical background or chemistry background, you all know that if you have an inorganic iron and some sulfur source, they can form iron sulfur cluster. It can be of 2 iron 2 sulfur type, it can be of 4 iron 4 sulfur type or 3 iron 4 sulfur type. But inside the cell, there is no such sink or source rather for iron sulfur cluster. Now, for the formation of the iron sulfur cluster, you need this current model of iron sulfur cluster biogenesis, where you can see a whole lot of proteins involved in that. So the iron and sulfur source is here in the mitochondria. It forms the 2 iron 2 sulfur cluster first, and then with all the help of this almost 30 proteins, one sulfur source comes out in the cytoplasm, and also from other iron source, it forms a 4 iron 4 sulfur cluster in the cytoplasm. And then with the help of all these transfer proteins, it goes to the apoproteins, which require the iron sulfur cluster for its activity. And here I have shown how this whole iron sulfur cluster biogenesis is conserved in higher eukaryotes, for example, from yeast to man. And here I can show you where the Viperine comes into picture. So the Viperine is one such apoproteins, for example, here. So the Viperine, apoviperine needs the iron sulfur cluster to show its activity or to block the viral DNA replication. Now, what I tried to understand during my postdoctoral research is that this particular pathway where the CR targeting complex composed of 3 different proteins, that's the CR1, MMS19, and CR2B, they basically help in the cluster to transfer from its previous protein to the apoprotein. So I try to understand whether it is essential for all these 3 proteins to be there for the cluster to be transferred, or one of them is enough for the cluster to be transferred by this pathway, or 2 of them. Also, the other thing which I try to understand is that there is a conserved tryptophan residue on the C terminus of this particular protein Viperine, and I try to understand what is the role of this conserved tryptophan. The other project which I worked on during my last postdoctoral research is to understand the mechanism of each of the cytosolic protein in synthesis of the iron sulfur cluster and its transfer to its apoprotein. So basically what I did is that I tried to purify all these proteins or the protein complex separately, or as separately as one proteins or as protein complexes, and then try to understand their mechanism by enzyme kinetic studies. So for today's talk, I will again not focus on this particular story, but I will focus on the other timbarel fold protein that is a part of the glycolytic mechanism. So here comes the other protein triphosphate isomerase, which I worked during my PhD in Bangalore. And this is a part of glycolysis, which is again a part of our respiration. So the respiration starts from glycolysis to TCA cycle to electron transport pathway. So here, if you see, try to see what glycolysis does, you can also think that glycolysis is also a similar complex phenomena as iron sulfur cluster biogenesis, as I showed in my earlier slides. But here, one fact you need to see is that the enzyme triphosphate isomerase is doing a chemistry. What chemistry it's doing? It's doing an isomerization where it's changing glyceraldehyde 3-phosphate, which basically is an aldehyde, to a ketone, which is known as dihydroxyacetone phosphate. So basically, it's doing a proton transfer and doing an isomerization from an aldehyde to a ketone. Now, if you forget about the upper part of this glycolysis pathway and the lower part of this glycolysis pathway, still, this enzyme can do this reaction. So this particular enzyme is not dependent on the other proteins for doing its chemistry, whereas the Viperine was dependent on the other 30 proteins for the generation of the iron sulfur cluster pathway, and then give it to the protein and then do its work. So from a biochemical perspective, we are more interested into the chemistry, how the enzyme is doing its chemistry. So when I started my PhD, I basically started to understand this enzyme and what it can do and how it can do. But honestly, I would like to share it with all of you, especially the undergrad and postgrad students, because probably you will be taking another step ahead for your PhD. Because when I started my work as a chemist, anything from biochemistry used to fantasize me. I used to be very happy to work with. But all the department people started asking me that what are you going to do with triphosphate isomerase? This is an enzyme. If you open any biochemistry book, you will see that everything has been done by triphosphate isomerase. So what new you can learn in a PhD by studying this enzyme triphosphate isomerase, which is a well-known example of a thin barrel fold. So with this question, I actually happened to go back to my PhD supervisor, and I also asked the same question that everybody is saying it's old, everything is known. So what new we are going to learn from this? So the reply he gave helped me a lot and still helping me a lot to go ahead in my future research career. So he said that it is known for everybody, even it can be known for us also. But the whole point of doing research is research. So if we can research something, so let's see, with this notion, I started my PhD, and I will try to let you through the story of my PhD thing and what I have learned from this well-known, well-studied enzyme triphosphate isomerase. So to start with, first, let's start with an enzyme architecture. So triphosphate isomerase is an enzyme. So basically it will catalyze this particular reaction, as I have mentioned, the isomerization between an aldehyde and a ketone. And for the enzyme, it requires a particular active site. So here you can see this enzyme, it has almost 250 amino acids. So the primary sequence has 250 amino acids on it. So it's not important that all the amino acids will be doing the chemistry. So it has its active sites, which are highly conserved, consists of 3 to 4 to 5 residues. In case of triphosphate isomerase, it's either 3 or 4 residues in the active site. Also, the enzymes are very much flexible because they're always kind of vibrating, and the substrate can go inside and then get stabilized, do the chemistry, and the product gets released. And also, it's interesting for any enzyme to check that the active site is mostly located near the dimer interface if the enzyme happens to be a higher order oligomer. So the multimerization is also very important. Now let's come back to the particular case of triphosphate isomerase. So again, I would like to remind you, as I already mentioned, so this is the ketone, dihydroxyacetone phosphate. This is the aldehyde, glyceraldehyde 3-phosphate, and both have 3 carbons. That's why it's triose phosphate. Both have phosphate moiety as well. That's why the name of this enzyme is triose phosphate isomerase. So it's basically isomerizing 2 triose phosphates with a ketone and an aldehyde groups. And this reaction is a reversible reaction. So when I started looking at this enzyme, we were trying to understand that how the sequence varies with time or with organism. So there are such databases available on the internet freely. One is the sequence database known as SwissProt or UniProt. And when we tried to find out how many sequences of triphosphate isomerase are there, which are unique. So they are from a particular organism, and the organism has not been duplicated in that whole set of scenario. So I have found out that there are almost 3,400 unique bacterial triphosphate isomerase sequences available in SwissProt database. Also, in the protein data bank, which is the structural database, I have found out that there are 32 structures already available in the PDB. So you can see or can understand from here that this enzyme is so vastly studied that already there are 32 structures available from different organisms. And to remind you again, the triphosphate isomerase is a classic example of TIM barrel fold. In fact, this TIM whole abbreviated form comes from the enzyme triphosphate isomerase with a beta barrel inside and the alpha barrel outside from the periphery. So I, with this knowledge, tried to probe the role of highly conserved residues in triphosphate isomerase using that 3,400 bacterial datasets. Now, what and how does the enzyme works? So the general mechanism is just a proton transfer. So for the proton transfer, you require a base, and then you require an acid for the donor, for taking the proton, and then giving the proton back. So by this is the simple chemistry for the formation of DHAP to GAP, that's the aldehyde, with the help of a formation of an intermediate which is known as an indiol intermediate, because here you can see the in moiety. Now the characteristic features of this particular enzyme, triphosphate isomerase, so I will be using either triphosphate isomerase or TIM for the same purpose. So the characteristic feature is that the catalytic residues of this particular enzyme is from the same subunit. And here I have shown you the 4 catalytic residues, and I would request you all to try to remember this name and numbers, because this will be repeating in my talk, and it will be easy for you all to follow the talk. So this is the glutamate 165, which is one of the catalytic residues. And this is the residue which acts as this catalytic base here. The other residues which are there present in the active site is the histidine 95, which acts as the proton acceptor and a proton donor again. This glutamate 97 and the lysine 12. So this lysine 12 is not doing directly anything to the chemistry, but it's more or less helping in the stabilization of this particular substrate. So the other characteristic feature of this enzyme is that it has a flexible loop. And why this loop is known as catalytic loop? Because most of this most important part of the enzyme chemistry and the active site, this glutamate 165 is basically situated in this loop 6. And this loop is quite flexible. And also there is a phosphate binding segment to keep this substrate phosphate part in a very rigid way, because nothing is happening towards the phosphate part, whereas the whole chemistry is happening on the C3 section of this particular substrate. And also it was known that it's a diffusion controlled reaction, and that's why it's an evolutionary perfect enzyme. So the enzyme basically cannot do any good for its rate, how the reaction is happening. So to check here, I can show you 2 different conformations as has been found out from protein extracrystallography, one in presence of the substrate and the other in absence of the substrate. So the open conformation which has been shown here in cyan is the one structure where there was no substrate on the active site. Whereas the closed conformation shown in green, that is the structure in the presence of the substrate. So here you can see that when there is a substrate, this closed conformation is more stabilized by the formation of extra hydrogen bonding interactions. And for this, there is a change in this particular glycine-rich area of this enzyme. And the difference between the loop open conformation and loop closed conformation is almost around 7 angstrom, which is quite a higher distance to go for an enzyme for doing its enzyme chemistry. Now, how does the enzyme work? So the proton transfer mechanism, there are 2 different mechanisms coming from 2 different labs. One from the well-known biochemist Knowles mechanism, which has been proposed in 1991, which is almost like 50 years back. So in this case, this glutamate 165 acts as catalytic base. So it takes the proton and then it forms the indiolate intermediate. And then this histidine 95, it acts as the proton donor. So when it acts as the proton donor, it basically changes this imidazole side chain to an imidazolate moiety. And then again, it takes the proton back from the glutamate 165 to form the aldehyde, that's the glyceraldehyde or GAP. And then again, they are all free for a second round of catalysis. Now, in this case, you can see that I have talked about 3 residues: glutamate 165, histidine 95, and lysine 12. They are the part of active site residues. Now, why there was another alternate mechanism came up from our research group. Now, why was the necessity of another reaction mechanism to come up first? So here you can see that if this histidine 95, that's the imidazole side chain, acts as the proton donor, then it has to go through a step where it forms an imidazolate ion. So here is a conversion from an imidazole to imidazolate. And if you think of your own chemistry knowledge, you will remember that this change from imidazole to imidazolate happens at a pK value of 14, which is a very high pH range. But in our cell, we are all living and our cells are probably around pH 7 or neutral pH. So then this happens to be a very energetically high or not so stable phenomena. So there comes the next opinion about an alternate mechanism where there is an extra involvement of this glutamate 97, which is also near around this active site. Rather, it's a part of the active site, and this particular residue also is fully conserved. In this case, the particular imidazole side chain of this histidine 95 does not have to go through that imidazole to imidazolic state. Rather, it goes through a imidazole to imidazolium state and then forms the gap. That's the aldehyde. The other chemistry remains the same. But here in this case, the change from imidazole to imidazolium, that pK is around 6.8, which happens to be near around the neutral pH of 7. So that's why we came up with this alternate mechanism. Now, the important fact about triphosphate isomerase is that if you take this protein from bacteria or eukaryotes, to get the active protein, it requires to dimerize. So the active triphosphate isomerase is a dimer in bacteria and eukaryotes, whereas it is a tetramer in archaea. And if we zoom in now to the dimer interface of this protein, here you can see a whole lot of residues which are very highly conserved. And in green, I have shown one monomer, and in the cyan, it's the other monomer. And the loop which protrudes from one monomer to the other monomer is known as the loop 3. So in this case, you can see that there is a residue called threonine 75 over here, which comes from the other monomer. And this residue is very highly conserved residue, and it also forms almost 4 inter-subunit interaction. And if you little bit try to focus here, that you can see here your already known residues, that's the histidine 95, the catalytic site residue, the glutamate 97, the lysine 12. So all of them are the part of active site, and they are coming from the other same monomer. That's here for the sake of understanding. Let's say this is from the green monomer, whereas this loop 3 or the threonine 75 is coming from the blue monomer. So to understand that, we did a bioinformatic analysis with all these 3,400 bacterial team sequences, and the amino acid diversity we are trying to see in different residue position. So through the x-axis, I showed the residue number, and as I have mentioned that there are almost 250 residues present in this particular amino acid, whereas the y-axis tells the amino acid occurrence. So what do I mean by this amino acid occurrence is that if you take a randomly any particular amino acid position, suppose for example, this 126 position, and here you can see the amino acid occurrence number is 1. That means that there can be only one type of amino acid present in all these 3,400 sequences. For example, in this case, this is cysteine. The other ones here on the upper side are most variable amino acids because they can have any amino acids in that particular site. So for example, this 41 site is here, which is quite high. And I also want to mention this fact that the number of fully conserved residues in this particular enzyme is 10, as shown here on the residue number basis. Now, if I try to see where are these fully conserved residues present, taking the structure of the triphosphate isomerase. So this is a structure solved from the Plasmodium falciparum enzyme. And all these stick ball which are kind of like coming out from this helical or the beta sheet structure are the fully conserved residues. And here you can see that all these fully conserved residues from this green monomer are quite inside the protein, whereas the threonine 75 from the green monomer, which is the loop 3-1 near the dimer interface, is actually outside. But this outside is the other dimer, whereas here the blue monomer threonine 75 is very near to all the other fully conserved residues from the green monomer. So this we need to kind of remember, and then we try to check that whether already in literature the role of these fully conserved residues are available or not. So we have found out that the active site residues, that's the glutamate 165, acts as catalytic base, already proven. Lysine 12 helps in positioning of the substrate, already known. Glutamate 97 also is an active site residue, as has been shown by the alternate mechanism. And histidine 95 also act as the electrophile or the proton donor, whose roles were already known. I won't go into the details of that. And then only one remains, that's the threonine 75, and its role was not so known when I started doing my PhD. So we try to find out or try to understand that what can be the role of this fully conserved residue. Now, knowing the fact that this is one of these residues which comes near the dimer interface, we try to think that maybe it has something to do with the dimer integrity of the protein. And since the dimer integrity was very much important for the protein to be active, we tried to zoom in this portion of the enzyme. So if I now try to zoom in to the dimer interface interactions, here I have shown you the threonine 75, whose role was not known. And I try to understand what are the neighboring residues of this particular fully conserved residue. I have found out that this residue forms 4 inter-subunit interaction with very important and highly conserved residues of the other subunit. Most of them are the catalytic one, for example, the glutamate 97 or the lysine 12. The other residues which comes near around, one of them is this glutamine 64, and the other one is this asparagine 10. They are also in connection with this threonine 75 directly by the formation of hydrogen bonding. So here we try to understand this particular network near the dimer interface. And the important fact about this particular lysine is that this lysine is directly connected to this glutamine 64. And if I try to see the phi-psi value, that's the dihedral angles of each of the amino acids inside a protein, which is very much required. And there is something called Ramachandran Plot, where you can plot the phi-psi values of each of the amino acids and then try to see if they are in an allowed region. So by allowed region, it means there is no sterical clash between any of these particular atoms. Whereas the phi-psi, that's the dihedral angle of this particular lysine 12, that's the one of the active sites, that falls in the disallowed region of the Ramachandran plot. So here we should remember that this strained conformation of this lysine 12 is very important for the enzyme to be active, because lysine is one of these active site residues. And for this, to maintain this particular phi-psi, this glutamine 64 should be very important, because this is making a hydrogen bond with the backbone CO of this particular lysine. So with this piece of information, we tried to again go back and look at our bioinformatic analysis of sequence conservation, where I have mentioned that there are 10 residues which are fully conserved. And we have found out to our surprise that this glutamine 64 also is a very highly conserved residue. Now, if I go back once more, the other residue which was here near the threonine 75 was asparagine 10. And if you try to see here what happens to the 10 residue, you can see here that is also a very highly conserved residue, which comes around n is equal to 3. So only 3 type of amino acids were present in that whole data set. Whereas for the glutamine 64, we checked and found out that there can be a possibility of 5 different amino acids present. And if you now see the percentage of amino acids present in that particular 64 position, it shows that almost 85% is occupied by the glutamine and 11% is occupied by glutamate. And the rest of it is valine or proline or histidine is only in 1 or 2 sequences among all these 3,400 sequences. So here you will probably be agreeing with me that either this is predominantly the presence of the 64 position is either by glutamine or glutamate. Now, if you try to think from a chemist perspective, the only difference between a glutamine and glutamate is that there is only a change of a CONH2, that's an amide moiety, to a carboxylate moiety, that's the COOH. So we found out that the number of PDB structures were available in the protein data bank, that's the 32. Among those 32 structures also, there were 29 structures which had this glutamine, whereas there are 3 structures which had glutamate at that particular position. So for my work, I focused on trying to understand the role of the fully conserved threonine 75, which is present in the dimer interface, and the highly conserved glutamine 64, which is again in the dimer interface. But we should remember that the threonine 75 forms interaction with this Q64 from another subunit. And both of them are from loop 3 of one subunit or the other. And for the sake of my study, I have used Plasmodium falciparum triphosphate isomerase as a template to do this mutational studies. Now, we wanted to understand what is the effect of mutations at 2 of these highly conserved residues, either 64 or 75. So the mutants generated, for the glutamine 64 study, I have changed the glutamine to either asparagine, where there is 1 carbon short of the chain, or to the naturally occurring mutant, that's the glutamate. So in this case of glutamate, is an isosteric replacement, but the hydrogen bond should remain unperturbed only if this glutamate is protonated. Then again, it can still form the hydrogen bonding. Whereas here, I have taken out 1 carbon unit apart, so there probably should be a hole near the dimer interface and the hydrogen bonding network should be perturbed. So that was our hypothesis to start with. For the other purpose, there's the threonine 75 mutational studies. I have made 4 different mutants. So either I have changed the threonine to serine. So here you can see that 1 CH3 moiety has been taken out when it's a change from threonine to serine, or to valine where there was no polar group on the moiety, or to cysteine, which is similar to serine, but instead of OH, you have the sulfur over here, and to asparagine. That's a change from only a CO and CH3 to a CONH2. So we wanted to see that what happens to the inter-subunit interactions which the threonine 75 was doing, almost 4 inter-subunit interactions. So whether by changing these residues, can we perturb the inter-subunit interaction? That was the question we tried to answer. Now, to characterize the mutants, I have used different biochemical or biophysical techniques. To start with, once I have cloned the mutant, I try to purify them using chromatographic steps. And once we get the purified protein, the first thing to do is to check the mass of the protein. That is to check whether I get the proper protein or not. So you have a calculated mass and then you do an LC-SI mass spectrometry to get the monomer mass of the protein. And in our case, we have checked with the calculated values, with the observed values for all the mutants. They were going together very nicely. So we have all the protein mutants in our hand to start the experiments. So first we try to see, because of these perturbations, what happens to the secondary structure of the protein. So we are actually changing the primary structure, that's the sequence, and trying to see what is happening to the secondary structure or the tertiary structure or the dimeric property of the protein. So first to start with, when we have monitored the far UV circular dichrometry study, so we found out that there was hardly any change for this Q64 mutants or T75S mutants. So here I have shown only 1 T75 mutants, but the other were also showed similar result. Whereas when we have recorded the near UVCD spectra, we have found out that the wild type is very similar to the T75 mutants, whereas there is a huge loss of tertiary structure of the Q64 mutants. Now, by near UVCD, we actually can predict whether there is any change in the tertiary structure of the protein. And as a control, we have used the wild type protein at a very lower pH where it has been put under acidic condition. And under acidic condition at that lower pH, protein normally it basically disrupts all its tertiary structure in the hydrogen bonding. So you can see here that from the wild type to the most highest disordered structure of the wild type, these Q64 mutants fall in between. So they are losing their tertiary structure as a result of this single point mutation in the highly conserved 64 position. The other experiment which we did to check the oligomeric property of the protein is analytical gel filtration. So in this case, to our surprise, because our hypothesis was that the threonine 75 makes 4 inter-subunit interaction. So if you change the threonine 75 to anything else, probably the inter-subunit interactions will be changed and there will be a difference in the oligomeric property of the protein. But to our surprise, we see that there is no change in the elution volume of the T75 mutants with respect to wild type. So they are all dimer in nature. So this was the starting point from where we tried to see some new things coming up from this widely studied enzyme. Similarly, the Q64 mutants, they showed difference in the elution volume. So if there is a higher elution volume, that means that your protein is coming out of the column late. That means that's a smaller protein. So for the Q64 mutants, it showed more of like a dimer monomer equilibrium. So as a result of the mutation, there is a probability of the formation of the monomer of this protein. So from these 3 different experiments, we can say that the Q64 mutants, they are more important for dimer integrity and the tertiary structure as shown from analytical gel filtration and near UV spectroscopy. Whereas the T75 mutants, for them, the dimer integrity and the structures are quite well maintained. Doesn't matter whether we have part of the T75 or not. Though the T75 takes part in 4 inter-subunit hydrogen bonding interactions. So then the next question would be then where is the difference or what it is doing? So to understand both the set of the mutants, so for example, let's start with the T75 one, which did not show any difference in the oligomeric structure. If we do an enzyme concentration titration to check what happens to the activity. So if I am going from a very low concentration to a high concentration, if there is no equilibrium between the monomer and dimer and everything is always a dimer, there will not be any rate change because the dimer is the only protein which is active. So in this case, you can see that with respect to the wild type, the T75 mutants are not changing its specific activity rate. Whereas also you can see that the particular rate of this T75 in mutant is almost low, almost like 4-fold low at any given concentration of the protein. Whereas the Q64 mutant proteins, they show actually a protein concentration dependence of specific activity. And when we try to find out what is the KD parameter of these particular mutants, we have found out that there is almost an increase of 1,000-fold of the dissociation constant of the protein. So that means that the perturbation on the 64th residue actually changed the dimer monomer equilibrium of the protein. So from here, we try to conclude 2 things. One is that the glutamine 64 shows a major role in dimer integrity, where any perturbation in this particular position caused a 1,000-fold increase in the dissociation constant of the protein, whereas the threonine 75 is not important for dimer integrity at room temperature, though it makes 4 different inter-subunit interaction. Now, the next question would be that what this particular glutamate and glutamine, in case of the Q64 mutants, what are they doing? So we tried to crystallize our mutants, and for the Q64E mutant, we could get a crystal and we could solve the crystal structure. And now if I try to compare my Q64E crystal structure with the wild type 1, we have found out that all the either the intra-subunit or the inter-subunit hydrogen bonding it was making for glutamine 64 is still there in glutamate 64. Now our hypothesis was that if this glutamate is a carboxylate, then probably it will break the hydrogen bonding, but if it is still a carboxylic acid that is with the proton, then it will still maintain the hydrogen bonding. So the thing which we would like to ask is that if I now do a pH titration of my enzyme activity, what happens to these mutants with respect to the wild type? And also I would like to mention here that since these particular Q64 mutants were not so nicely structured, as you could see from the near UV CD, it was very difficult for them to crystallize. So after a lot of screening, I could get a crystal for the 64E mutant, but I could not get a crystal structure for the Q64N mutant to check what happens to that void position of this particular region. Now, if I do a pH titration, here you can see for the wild type that at higher pH, once it reaches the pH optima, which is around 7 pH, it remains same till 8 or 8.5. Whereas if I do the same experiment for the Q64N and Q64E mutant, we can see here that the Q64E mutant is losing its activity right after the optima. Even the rate of losing activity is higher with respect to the Q64N mutant. So in this case, our hypothesis was right, because when I am going towards a higher pH, the glutamic acid will be glutamate. So the pK2 of this Q64E is different with respect to wild type or Q64N. So this shows that change in pH actually perturbs the pK2 of the enzyme. So this was the importance of the glutamate. And what happens to the asparagine mutant? So since we did not get a structure, we tried to model the asparagine on the wild type. And when we modeled it and tried to see that for each stereochemically acceptable conformer, in each and every case, we could see that the hydrogen bonding with the backbone of the active site lysine, which was falling in the disallowed region of the Ramachandran plot, is actually lost. So for all the conformers here, you can see that this particular hydrogen bonding is lost, and that is probably the cause of showing the lower specific activity of this asparagine protein. So this shows that the residue glutamine 64 is very much important for maintaining the complex network of hydrogen bonding interaction near the dimer interface, as well for the optimal dimer stability in the room temperature. But it's very important for maintaining the dimer monomer equilibrium, because we have seen that when we change the glutamine either to glutamate or glutamate or asparagine, there is a huge change of 1,000-fold in dissociation constant. And the drastic loss in activity is probably important for the dimer integrity. And we can understand that how Q64 is important in protein activity. But not doing anything with the dimer stability, then what is its role? So here you can see that I have shown the different interaction that threonine 75 is making. So on my left side, these are the hydrogen bonding interactions it's making with the highly conserved and the active site residues, also with the glutamine 64, which we already studied and discussed. And the other interactions, that's the weak interactions which this threonine 75 is making, is the van der Waals interaction. So again, when we check this van der Waals interaction, all the residues which are coming up from the other monomer is either 25 to 4 different other residues. What happens to the active site geometry? So from the crystal structure, I solved all this crystal structure, and we found out that there is no such change in the active site conformation of these active site residues. So there is no conformational change, but there was change near the site of mutation. So here again, if we zoom in with the wild type enzyme, we can see it forms all these interactions, either hydrogen bonding or van der Waals interaction. But for example, when we change this threonine to the threonine 75 to asparagine, all these interactions, especially the van der Waals interactions, are lost. So there is a loss of interaction between the asparagine 75 in case of the mutants and the catalytic residue, that's the lysine 12. So that is one of the cause of the drop of this T75 in specific activity when we were trying to check what happens as a result of perturbation in this threonine 75. Also, the van der Waals interaction with this lysine 12 has been perturbed as a result of this threonine 75 mutation. And all the other proximal residues are either from the active sites or very highly conserved one. So then only the last question which remained here, that if it is not doing anything with the activity very much, neither it's changing the dimeric property, dimer monomer equilibrium, dissociation constant, then what it is doing? So we try to see that if threonine 75 is so much connected with van der Waals interaction and hydrogen bonding interactions near the dimer interface, which has all these active site residues, we try to check what happens to the temperature dependence of the activity. And when we did that experiment, that gave the answer that why threonine 75 is important. So if you see here the comparison of the specific activity at higher temperatures of the wild type with respect to all the other threonine 75 mutants, you can see that the temperature optima is kind of changing in case of the mutation. So at higher temperature, all the threonine 75 mutants were falling apart to show its activity. That is because of the perturbation near the threonine 75 as well as because of the perturbation of this weak van der Waals interaction as well as the hydrogen bonding interaction. So here I would like to tell that the sequence selection is at this particular position was very much important for the optimal temperature dependence of activity. Now to summarize this threonine 75 part, so I would like to say that when the threonine 75 has been changed to asparagine, there is a loss of hydrogen bond with the active site as well as there are loss of van der Waals interaction with the other catalytic residues, which causes the loss for the T75 in mutant, whereas there was no change in the active site conformation for the T75 mutants, at least in the dimer stability zone of greater than 0.1 nanomolar concentration of the protein. So it didn't show any concentration dependence of dimer monomer equilibrium. But the threonine 75 indeed was more important for the role in its enzyme activity at higher temperature. So to go back to the objective from where we started with, we tried to understand that if threonine 75, which is an interface interaction making residue, almost 4 intermolecular or intersubunit hydrogen bonding interaction, will probably be more important for dimer stability, whereas the glutamine 64, which was forming a hydrogen bonding interaction with the lysine active site residue, will probably be important for the activity of the enzyme. At the end of our experiments, we have found out a bit different results. So for the glutamine 64, that's the role of the 64th residue, was more towards the dimer integrity, whereas the threonine 75 was not the case. Whereas the threonine 75 was more important for the temperature optimization of this particular enzyme. So the result we have found out with respect to the objective was quite opposite, especially in case of threonine 75. Now I could finish my talk over here, but for the students, I thought I would like to show them one more biophysical technique which could be used to study normal biochemical enzymes and what can we find out from that particular technique. So the technique is again mass spectrometry, here in this case protein mass spectrometry, and the same mutants I have taken to understand what is happening for these mutants in the liquid phase and then what is happening to them in the gas phase. So whatever results till now I have discussed either was coming from liquid state for all the experiments except for the structural part where we have crystallized the protein. So basically it has been changed to a solid state. That's a snapshot of a particular time zone. In the case of nanospray ESI mass spectrometry, we try to see what is happening to the protein in a vapor phase as well. So for nano ESI, you keep all the voltage and the flow rate very low so that there is hardly any change in the tertiary structure of your protein, and you try to understand the oligomeric nature of the protein. So basically it should mimic what it is in the liquid phase. So if it is a protein which is a dimer, if you do a nano ESI MS, you should find a dimer mass. Now, the whole mass spectrometry can be divided in different compartments, and you can change the energy distribution depending on what you are changing in your machine. So if you kind of change this energy distribution, you can also make it happen that the dimer, you are trying to break it by the use of energy. So we try to see that if we start from a very low energy, whether we can still see the whole dimer for the wild type. And then if we increase the CID, that is that we are increasing the energy to break this dimer monomer equilibrium, we try to see what are the adducts we are checking in the mass spectra. So if it's a loose dimer, then it will break at a lower energy. If it is a very rigid dimer, it will not break, doesn't matter whatever the energy you are using. So we know that the wild type triphosphate isomerase is a dimer. Doesn't matter which concentration you are going and how much energy you are giving. So here you can see that we have done a titration from 40 electron volt to 120 electron volt. And in the 40 electron volt energy, you can see that there is only dimer of the wild type available. That is the active state of the triphosphate isomerase. Whereas when you increase the energy, there is a very small amount of monomeric mass coming out, which is increasing with the increase in energy. Now, if we fix one such particular CID values and then try to see how the mutations at the 64 position or the 75 position is changing this dimer monomer equilibrium. So here we have fixed this 80 electron volt. So in this case, the second one. So we kept this electron volt fixed, and now we are changing the solutions. So first the wild type and then the mutants. So here you can see that for the wild type, this 80 electron volt shows a very high amount of dimeric population as well as a very low amount of monomeric population. So indeed, the wild type enzyme is a dimer. Whereas for the Q64 mutants, you can see that there is hardly any dimer you can see at this particular energy, whereas the most of the population is monomer. So was the case for Q64N. And this goes very well along with our liquid phase concentration dependent specific activity rate as well. So if the enzyme is in a monomeric state where the wild type is in the dimeric state, obviously the wild type will show activity and the monomers won't. Now, if you check the T75S at this particular energy, so this is just an example of this threonine 75 perturbation. Here you can see also a dimer monomer, but the population of dimer is much higher with respect to the Q64E or Q64N. So this goes very well along with our liquid phase enzyme kinetic study. And from this particular study, we can tell that also in the gas phase, the dimer stability goes along with the wild type with the most dimer stability. Then next comes the threonine 75 perturb mutation, and then comes the Q64 perturbation. So again, from this study, we can tell that the Q64 perturbation was the most important perturbation for the dimeric stability of this protein. So with this, I would like to conclude my talk that though we knew that we know many things about these proteins, and from just the bioinformatic analysis, we could think that the threonine 75, which is fully conserved, making 4 inter-subunit hydrogen bonding interactions, actually was not so important to keep the dimer intact, but it was more important for higher temperature optimization of the enzyme activity. Whereas the 64th position, which is also a very highly conserved position, is actually more important for the dimer monomer equilibrium, though it only makes 1 inter-subunit interaction. So I still feel that what my supervisor said and the way we did our study is actually tell this fact that the selective pressure shaped the team's sequences and the temperature dependence of enzyme activity and the dimer dissociation constant. So there are still things to learn about this widely studied enzyme triphosphate isomerase. For my case, it was from the Plasmodium protein. It can be happening from other organisms also. So with this, I would like to conclude my talk, and I would like to thank you everyone for your presence and patience. And I would also acknowledge my PhD advisor, Professor P. Balram, who guided me all through this whole story, which I shared with you today. And I would also like to take this opportunity to thank Professor Hemlata Balram, Professor Invi Joshi, and Professor Imarin Murthy for being the collaborators and for letting me use their lab, and also for their enormous number of nice interactions with them. I would like to thank IIC Bangalore, CSIR for funding, and MBU mass spectrometric facility in Bangalore. I would also like to thank Professor Roland Lil, my last postdoc supervisor, for letting me work in his lab and learning new things about iron sulfur cluster proteins, and Philipp University Marburg in Germany and DFG for their financial support. I'd also like to thank all my colleagues from IISc, JNCSR, or Marburg for being there for many scientific interactions. And last but not the least, and most importantly, I would like to thank the webinar series committee member for taking care of such seminars in such a nice way in this particular time of pandemic. And I would like to thank the Department of Chemistry of GGDC Shingur, especially Dr. Amrit Kumar Mitro, for inviting me to give the talk. And thank you, everybody. I would be happy to take any questions.
Yeah. Uh, Hats off to you, dear Dhibarati. What a presentation.
Thank you so much.
It is always a great pleasure listening to you. Thank you very much for delivering such a wonderful lecture. You have enriched all of us through your mesmerizing presentation. Thank you very much. We have some questions for you.
Sure.
Should I proceed?
Sure.
Okay. The first question is, how could you mutate the amino acids so precisely?
Okay, so I think probably it's coming from somebody from chemistry, because I also had the same question when I started. So I would like to explain it a bit more, but do I have anything to show? Probably not. Okay, but I can try to explain. So you have an amino acid sequence, suppose A, B, C, D, and you try to change a particular amino acid, suppose the third one, which is, in our case, suppose it's the third threonine. Now, the way the protein gets synthesized inside a cell is a little bit different. So it's not like amino acid synthesis, where you get the amino acids and you synthesize the peptide bond in the test tube. So in protein biochemistry, what you do is you basically collect the gene of your protein, and each gene has a DNA sequence, has a nucleotide sequence, and there are something called codon. So you have 3 DNA base pair sequences from which one amino acid gets formed during the transformation. So replication is DNA to DNA, but translation is DNA to protein. Yes, DNA to protein. So what I do is I try to see from the gene level. So you can basically how to say it, you can basically isolate the gene of a protein, and then you can change these 3 codon pairs in such a way that it's now a codon pair of your changed amino acid. So suppose if it is a tryptophan, it is a thymine guanine base pair, and if you want to change it to, suppose, to a lysine, it's a alanine base pair. So basically you try to order a primer which starts with little downstream portion of your DNA sequence, and then you change this particular 3 residue positions of the DNA, and then again remaining should be the same as your wild type. And basically the idea is to do a polymeric chain reaction when you take your wild type template of DNA, and this small synthesized changed DNA should come and sit on top of it. So there will be a hole where is no hydrogen bonding, and it will keep polymerizing. So then you can top off this template DNA and form the new DNA which has the changed codon. And when that gets translated inside the E. coli, it gives you the new amino acid. So this is a very well-known technique in biochemistry. So probably if it is coming from some student, I would recommend that maybe you can go back and try to read about recombinant DNA technology and polymer chain reaction. I'm sure there are lots of videos which will probably give you a better idea about this.
Okay,
Was it
thank you.
understandable?
The next question is, what is... Yes, yes, yes,
Yeah.
yes, yes. Yeah, and the next question is, what is pathogenic mutant?
Okay, so the pathogenic mutant would be something where you change such kind of amino acids which gives you either a defect in your system. So for example, if you take a human protein and you change a mutational change an amino acid to another amino acid, and that causes a serious damage in your system, in your whole cell, or the enzyme cannot work, that could be something which can be called as pathogenic mutant.
Okay, okay. Thank you. The next question is from our principal sir, Dr. Shantanu Chakraborty. He is asking,
Yeah.
this enzyme of glycolytic path has a very important role in cancer cellular transformation. As we know, cancer cells show higher glycolytic activities.
Right.
Did you consider the mutants in relation to cancer?
Not really. And thank you so much for such a nice question, because it is true that glycolysis is very much important with respect to Woodburg effect. But for my purpose of the study, I did not check such things. So I just did the biochemical studies from this, but I'm sure it will be a very nice thing to look upon in future. Thank you so much for this idea.
Okay. Okay. And the next question is from Dr. Kollol Bera. You know Kollol, na?
Yes,
So
I know
this
him,
question
yeah.
is from Dr. Yes. So this question is from Dr. Kollol Bera. What are the parameters to engineer an efficient artificial enzyme?
Okay. So first of all, thank you, Kallul, for last seminar's talk. I heard it and it was really nice. And for this, I would think that probably you were talking about directed evolution. So I can tell you that I am not an expert in direct evolution, but at least with respect to the Tim barrel fold and especially Tim, I have read some literature where people try to understand the correlation between these conserved amino acid residues. So it can happen that you know that suppose there are two different same fold protein which does the different reaction. For example, here uh, if you could see my cursor here, so this 5-AHE, let me go to this state. Yeah. So this 5-AHE, this is a histidine biosynthesis pathway protein. And people have actually engineered from this particular protein another Tim barrel fold protein, which helps in tryptophan biosynthesis. And the only difference those two protein had was the difference in the substrate specificity. So basically the pocket where the substrate is going and sitting has to do with this whole chemistry. So when they have changed this particular pocket to small amino acids, so that now the pocket is little more of volume, then the other substrate from the tryptophan biosynthesis pathway could actually enter on this particular template and do that reaction. So I think that could be something to think of when you are trying to engineer another function on a protein. Also, since I like the sequence conservation thing very much, I think that there are conservational like conservational connection between different residue position. So I think it's more important to understand that which residue is connected to which residue, and if there are such 2 or 3 residues which actually keep changing. Sometimes we focus only on one, but most of the cases it's like if one changes, the other is also changing for the accommodation of substrate and eventually the function. So I would think those are the things which people should take care of if they try to think of doing a directed evolution. But saying that, it's not so efficient. So you need to check a lot of other parameters for sure to get some directed evolution protein like Francis Arnold always does.
Okay. Okay, thank you, Dhibarati. The next question is from Dr. Anupam Nayak. He is asking, what are the general characteristics, features of mutant?
So it can be very different depending on what kind of study you want to do. So the whole story which I showed today was everything done in vitro. That's outside. So basically, I just get the protein synthesized inside bacteria, and then all the experiments I did in vitro inside the test tube. Whereas there can be studies which are done inside cell. So you can also put these mutants inside living cells and then try to see what are they doing. So I would think that that would be more important to do, to check from a mutational perspective, that when you are doing in vitro, you know what are the changes it's doing from a biochemical perspective. So what are the change in function, activity, or very local function, local activity, local structural change, or from a global perspective. But when you are doing an in vivo analysis, that would most likely tell something about the function which the protein is actually doing in the cell. So suppose, for example, team from us, like from human, there are examples of mutants of particular residues which has been mutated. Suppose, for example, the 104 residue position in human team is glutamate. But there are studies and clinical results found out where this glutamate has been changed to aspartate in the allele level, in the gene level, and the person who is born with this mutational defect actually has anemia and very much neurodegenerative diseases. So I would say that there are two different perspectives of this mutational analysis. So if it is from the in vivo side, it can cause disease, or it can changes the whole protein structure and its functionality. Whereas if you do in vitro, these mutational studies mostly tell you what is the structural changes or the biochemical or biophysical changes or the activity changes happening in a protein.
Okay. Okay, Dhibarati. The next question is there any visible change after mutation?
Visible change with respect to what? Was there any such? So
No
maybe,
such
okay.
specification is there.
Yeah, so maybe I would try to answer it the way I am understanding it. So to visualize anything in protein level, you need a protein structure. So basically, you need an extra crystallographic structure of your wild type protein and the mutant protein. So for example, when I showed the crystal structure of different mutants, for example, here, so this is my crystal structure after doing the mutation from Q64 to E, that's the glutamate. I try to see if there is any change in the overall structure. So the overall protein structure was not changed. They were still the team barrel fold, but there, for this case, the Q64E case, there was not such change here near the zone of interest of mine or the active site residues. Whereas for the T75 mutant, I show that actually you can see changes over here. So if you minutely check in this particular case, that what visual change you could see as a result of mutation is that, suppose for example we take any of this hydrogen bonding. So this is my wild type where there is no mutation. So there is a hydrogen bonding between this threonine 75 and this asparagine 10. And when I change this threonine 75 to asparagine and then got the crystal structure, you can see this hydrogen bonding is still there. So this is my asparagine 10, this is my new asparagine 75. This hydrogen bonding is there. Whereas the van der Waals interaction here, if you see the distance is almost 4.71 angstrom with respect to 3.4 angstrom in case of the wild type. So those are the kind of visual changes you could see. Otherwise, I would say that all these techniques are actually kind of giving you the visual way of looking at it. So when you see that there is a change in the elution volume of your protein solution, you know that there is a change in the dimer monomer equilibrium. So in your head, you already know that in the solution, the wild type and the mutant are behaving differently. So in the case of mutant, you have more dimers or all dimers, whereas in the case of mutant, you have a dimer monomer equilibrium happening with time. So those kind of visual changes, for sure, we could see by this kind of mutational studies. Yes.
Yes, yes. Okay, okay. Thank you. And the next question is from my end.
Yeah,
You
sure.
showed sequence analysis. You showed sequence analysis taking all bacterial enzyme, right?
Yes.
But you did experiments on Plasmodium enzyme, which
Mm-hmm.
is a eukaryotic one.
Yeah.
So why? What is the logic of such discrepancy?
Yeah, so this is a very good question actually, to think of that somebody is doing the